Okay, in problem 12.23, we want to find the escape speed from the asteroid Dactyl. Okay. They tell us that its radius is only 700 meters, so it's not a huge asteroid. And its mass, although it's a large mass compared to you and me, it's still not a big mass compared to, say, the Earth. It's like maybe, what, a trillionth, a quadrillionth of the Earth. So we're going to find out. They give us an example, but it's just something we've covered before. So we're going to calculate the escape speed of to leave the surface of Dactyl. Okay. And they give us a clue it's going to be pretty small. So we're going to start with our speed. We're going to start with looking at the energy on the speed on the surface of Dactyl. Okay. So when we're on the surface and we're leaving, we're going to have some kind of kinetic energy because that's what we're going to have when we start. And it's going to have some gravitational potential energy. When we leave, you know, it'll have some of both also. Make these prime. We know that for the minimum escape speed, at the very end, we get really, really far away. We're going to be really, really far away so that we're going to have, first we're going to have our energy here, 1/2 mv squared plus g m1 m2 over r. And remember, that's negative, so we're going to put a negative in front of that. Okay. Equals, okay. At our escape speed, our minimum speed, our velocity when we're really far away is going to be 0, so it's going to make our kinetic energy 0, and that means that we're really far away, we're going to be infinitely far away, so it's going to make r infinite, and that's going to make our gravitational potential energy 0 when we're that far away. So what that means for us is that these are going to be equal 1/2 mv squared. It's going to equal g m1 m2 over r. Okay. At the escape velocity. If we go a little faster, then we'll have a little energy, or we won't have to get all the way far away in order to get that to happen. Okay. Now, one of these m's divides out the mass of the person or thing that's leaving the planet. That's this one and this one. Okay. That leaves with the mass here. So if we derive that back out, okay, we're going to keep these. We're going to move this over to the other side. We'll take the square root. V equals 2g m2 over r, and the square root of all that. And if you look at the constants, I write it out here. It'll be 2 times 6.67 times 10 to the negative 11. That's newtons meters squared over kilograms squared. Okay. This is going to be that mass we talked about up here. It's going to be 3.6 times 10 to the 12th kilograms. G, so it shows up better. Good. We're going to divide that by 700 meters. When I calculate all that out, I get an answer of 0.83. Okay. My units left are going to be newtons meters squared over kilograms squared times kilograms. Leaves me with newtons meters squared over kilograms. Divide out of meters. I have Newton meters divided by kilograms. That actually leaves me with meters squared over seconds squared. And that's going to, when I take the unit, it's going to take the square root, it's going to leave me with meters per second. Second part of the question asks, could a person reach this speed just by walking? The answer is, yeah, it's pretty slow, 0.83 meters per second. It's about 80 centimeters per second. That's pretty doable. Okay. So again, it's pretty small. Again, it's a slow speed, but it only happens because we have such a small mass, again, comparatively speaking to a planet, and with such a small radius.